Hi, for this short video, what we want to do is cover the first part of Chapter 6. Chapter 6 deals with network optimization problems, and the first section of it deals with what's called the minimum cost flow problems. Now, these are really the most robust set of network optimization models. It involves basically when you are moving items across a network from one set of locations to another typically, and you're trying to do so at, say, a minimum total cost. Uh, the transportation problem that we saw in earlier chapters is really just a special case of this minimum cost flow model. So what we want to do is cover the example in the chapter, and then I'll show you the Excel file associated with that example and point out some special features of it. So the problem that's presented in the chapter is this distribution unlimited company problem, and basically it's summarized as follows. We've got two factories that each produce some number of units each. We have demand. Let me take care of that. We have demand at two separate warehouses that require a certain number of units for each. And then it turns out we have sort of a middle point, a distribution center that we can ship product to from the factories and then ship it out to the respective warehouses. However, there's also direct ways to ship from the factory to the from a factory to a warehouse, and that is by a rail link. And so we have unlimited capacity on the rail links, but if we ship to and from the distribution center, we have a maximum capacity that we can ship, that being 50 units for each leg of that journey. So the optimization problem is really to identify, how many units, which in this case, by the way, is truckloads, should be shipped along each shipping lane. In other words, how many should go direct from the factory to the warehouse by rail, and how many should take a route through the distribution center, but the transportation being offered by truckloads. So let's take a look at the way this network is set. So again, we've got factory 1 and factory 2 on the left with the associated amounts of available units that can emerge from each of those factories. And on the right, we have the warehouses that are demanding a certain number of units. And as you see, this very top link is we have the ability to ship directly from factory 1 to warehouse 1 by rail. We also have the ability at the very bottom to ship directly from factory 2 to warehouse 2, again by rail. Now, we mentioned that there's a distribution center sort of in the middle of all this, and we have the option to send truckloads from factory 1 to the distribution center or from factory 2 to the distribution center, and then we can ship from the distribution center to either warehouse 1 or warehouse 2 there on the right. Now notice there's, the products are the same, meaning the products are interchangeable, the ones that are created at factory 1 versus the ones that are created at factory 2. So we're really only dealing with sort of one type of unit, one commodity, if you will. So this is one way to display the distribution network, again, using the little icons to really symbolize sort of the various modes of transportation. Here's sort of a more just numeric description of the network model, but now we've added some data. We still have the amounts produced from the factories and the amounts demanded by the warehouses, but now on each of the arcs, and an arc is represented as a connection between any two locations in the network. So for example, this top arc connects from factory 1, F1, to warehouse 1, W1. And so this very top arc, again, it's an arrow with a head on it implying a particular direction that the units can flow. And we've also got a cost now associated with that arc of possible flow. And what that means is for every unit that we send from factory 1 to warehouse 1, we'll incur along this direct rail line at the very top, we'll incur a cost of $700 for each unit. So each arc now is characterized by the cost to move one unit along in the direction of the arrow. So you'll see that if we go through the distribution center, we'll have to incur, two separate truck lane movements. So if we go from factory 1 to the distribution center, we'll incur a $300 per unit transportation charge. If we move from factory 2 to the distribution center, we'll incur a $500 unit. And we've again got particular cost per units for the outbound lanes out of the distribution center. Now there's one other set of data in addition to the costs, and that is the capacity. So we have a maximum of 50 truckloads that can be sent along any of these lanes. So that's given in the square parentheses, and that is a 50 units maximum that we can ship along the lane from factory 1 to distribution center, or 50 units max from factory 2 to distribution center, and correspondingly the outbounds from the distribution center to either warehouse 1 or warehouse 2 also carry a maximum of 50 units. Now, here's sort of a more sort of network type of representation of this model, sort of a network formulation, if you will. We still have identified all the nodes, F1, W1, F2, W2, and DC, the distribution center. But now you'll see in square parentheses next to each node is the representation of the amount of capacity available in the case of the factories. But you'll notice these negative numbers corresponding over here to each of the warehouse nodes, the minus 60 on W1 and the minus 90 on W2. Now, basically, what those numbers represent is the amount of units that are either sort of generated and put into the network by the factories. In this case, they're positive values. And for the networks, it's the amount of units that must be sort of pulled out of the network. In other words, we view the factory 1 and factory 2 as supply nodes because they're supplying units into the network, and W1 and W2 as being demand nodes where they are needing to consume or absorb units from the network as their final destination. Now you'll notice the square parentheses around the distribution center have a value of 0. This is typical of what we call a transshipment node, and that is, product is neither created at the distribution center or consumed at the distribution center. It's really just sort of a pass-through location. You think about it. Again, that's a typical function of a distribution center, is to bring shipments in, maybe consolidate them, mix them up, change them, or whatever, and then send them out the other end. They don't actually create or consume units in that way. We still have our capacities associated with the truckload arcs, and we also have all of our per unit transport costs labeled on this model. So this has all of the data that we need now to formulate and solve this particular model. Now, a couple of things about these minimum cost flow models, and we've talked about them so far, and that is they're represented again by a network. And the network consists of a set of nodes, which are the circles in this case, and arcs, which are the connections between those nodes. Now, again, each node where there's a net amount of flow generated is a supply node. Each where there's a negative amount of flow generated is a demand node, as in the case of the warehouses. And we talked about that transshipment node is the one that has sort of neither a supply nor a demand for the network. It's just a pass-through point. And by the way, such nodes have to obey the law of conservation of flow, meaning the total amount of products that you ship into a distribution center must equal the total amount of products that you ship out of the distribution center. And then finally, again, we've got maximum amount of flow through an arc. So that represents the capacity of that particular arc. So again, anytime we have this minimum cost flow problem, again, at least one node must be a supply node or there's no capacity or no ability to put products into the network. And in this example, we have actually two supply nodes. And again, another rule is that at least one of the nodes in the network has to be a demand node. In this case, we have two demand nodes represented by the warehouses. And if you're not a supply node and you're not a demand node, then you are a transshipment node, basically. And again, we've got flow that goes in only one direction across an arc as represented by the arrowhead. Now, if you had the ability to ship sort of either way between two nodes, then you would have basically an arrow pointing each way, two separate arcs, if you will, each with its own potential capacity and each with its own potential arc flow cost. So again, key thing is that you have to have enough arcs to be able to actually sort of make it happen. In other words, it has to be able to have sufficient connections and sufficient capacity to actually meet all of the demand from the supply nodes. And again, one other key thing is that when you flow units across an arc, it's basically a linear multiplier. In other words, it's however many units you ship across that arc times the cost per unit to ship across that arc. So it's not nonlinear or anything like that. It's just simply proportional. If you send twice as many on that arc, your cost is going to be twice as much, basically. And the overall objective here is to minimize the total cost of, again, meeting the demand across that network. Now, a couple things is that, it'll have a feasible solution if and only if the sum of the supply from the supply nodes equals the sum of the demands at its demand nodes. In other words, that we have to, if we're off in either direction on that, either too much capacity or too much capacity or too little capacity relative to demand, then the model that we'll be showing you will be infeasible. Now, you can have a situation where you've got more capacity than what you have demanded, but in that case, you just have to basically limit the amount that can emerge from the supply nodes, and you have to send at least an amount that's demanded to the demand nodes. And this last point is really not that important, but just so happens that if you have like integer values for all of your data, then it turns out your solution will indeed be integer. So let's take a look at now the spreadsheet model. So I'm going to shell out over here to Excel and talk about some of the characteristics of this model. Now, first of all, on the right, as with all the examples in the book, we've got the range names and the cells. So we've got the range of capacity, which is given in this F5 through F8 right here. We've got the from nodes, that's the list right here, F1 down to F2, which is again represented by cells B4 through B9. We've got the net flow in column J. Again, these are all named ranges. We've got the nodes listed in I, in the I column. We've got the shipment amounts, which are actually our decision variables here in bright yellow. This is what we're trying to decide, is how many units should we ship along each arc in the network such that we meet the demand by the demand nodes. So again, those represent this column D, which is again our ship amounts. Those are our variables that we're trying to solve for. We've got supply demand in column L. This is data. This is those numbers corresponding to each node, which says whether or not it's a supply node, as in the case with the positive values for factory 1 and factory 2, or it's a demand node, as represented by the negative numbers, the negative quantities required from warehouse 1 and warehouse 2, or if it's a transshipment node, which was the case for the distribution center. So again, this is all data straight from our network representation. And again, like we said, all nodes, each node is either a supply node, a demand node, or a transshipment node. So we've got the supply demand there in column L. We've got the two nodes in column C. So we've got sort of these two columns, the from and to, are just simply identifiers to say what node are you moving from to. In other words, each of these combinations from F1 to W1 represents an arc in the network. So you'll notice there's a total of 6 arcs in the network. Factory 1 to warehouse 1, which was was the rail route. Then we've got the 4 arcs that go into or out of the distribution center, represented by these 4 right here. And then we've got the final direct rail connection between Factory 2 and W2. So again, these named ranges of the from and to are just simply identifying the nodes at the outer ends of each arc. The total cost is D11, which is a sum product of how much you're shipping, how many units you're shipping on each arc of the network, times the unit cost for shipping along each of those arcs. And that's the final range, by the way, which is G4 through G9, which is, again, just pure data. Now, we have capacity values here in column F, which were for those trucking lanes, at most 50 trucks along each lane. So again, we've got now a descriptive model, which means we could, put in any values here. We'll just zero these out. And so now we're asking the model to meet the demand, which in this case we're not. We're sending 0, there's nothing being shipped over the network right now, which means we're not meeting our demand here at the warehouses. Our net flow in this case is in fact 0, but in fact we need to actually send 60 units to warehouse 1 and 90 units to warehouse 2. So that's how we'll ask the solver to solve this particular problem. Now, let me talk about the constraints before we sort of dive into the solver representation. So again, from an optimization standpoint, we're trying to minimize the objective, which is total cost. And our changing cells, our variables, are the amounts we're going to ship along each of those arcs. But here's some of the constraints associated with this. First of all, we must meet the net flow for each of the nodes. So in other words, we must have 80 units that come out of Factory 1, and we must have 70 units in total that come out of Factory 2. Similarly, for the demand side, we must have 60 units go into Warehouse 1 and 90 units to go into and be absorbed by Warehouse 2. And we need pure conservation of flow for the transshipment node. So we'll show you how these constraints play out here. All it's saying is that, again, we've got these values in column J must equal the net input or demand pulled out of the network. So the other constraints, by the way, are just simply these arc constraints related to each of the trucking lanes, that you can ship at most 50 truckloads against each trucking lane. Now, so, that's just pure data. That's pretty easy. We've got non-negativity constraints. You can't send a negative amount over a given arc. But the only thing I want to kind of hone in here and look at a little bit carefully here are these representations for the net flow. Now, the net flow basically consists of the following. If you look up here in the formula, it's basically the sum of all the flow coming out of a node minus the amount of sum flowing into a node. And probably the easiest one to kind of start with would be this one right here, the distribution center. So what we know is that again, the sum of the amount going out of the distribution center minus the sum of the amount going into the distribution center must equal 0. That's that conservation of flow. Now, in the formula here, we're using this sum if. In sum if, you may be familiar with this particular function in Excel. If not, let me explain how that works. In sum if, we basically choose the arguments are the following. You've got sum if, you pick a range, you pick a value that you're testing for within that range, and then you are asking it to include in the summation a value of a given sort of range as well. So here's how this works. What we're saying is the following. What this is saying is the following. If in the range B4 through B9, which is this from range, that's, again, it's a named range defined over here on the right. If the value in that range is equal to DC, which in this case there are 2 in here that have the values DC, then include within that sum the corresponding values in the ship range. So again, take a look at it. That's sum if the from range, but we're looking for the value in I6, which is the letters DC, and then it's saying the thing to sum up will be in fact the values corresponding in the ship range. And so that's the amount basically coming out of the distribution center node, and you're subtracting from that another sum if amount, which is basically the following. Now it's looking at this 2 range, and it's saying if in this 2 range you've got the values DC showing up anywhere, then include those 2 values within your summation. So in this case, I need to say this and this. So it would basically be summing those 2 values, which again, those are that's the sum of basically the arcs that are that are coming into the distribution center. So again, this expression here in column J corresponding to DC is just simply the sum of the flow coming out of the distribution center minus the sum of the flow going into the distribution center must in fact, in this case, equal 0. It's got to observe that conservation of flow. Now, as you go to these other nodes like the factory, again, it says the amount coming out of the node minus the amount coming into the node must equal exactly 80. Well, it turns out there's 2 arcs that are coming out of factory 1, so it's going to sum those up to represent the amount coming out of that node. But you'll notice there are no arcs that are coming into factory 1. So it turns out there's not going to be anything to sum in that case, and it'll just be a value of 0. So this will then represent, like for example, if in fact we send 5 units from factory 1 along the rail line to warehouse 1, and we send 15 units, say, from factory 1 by truck to the distribution center, you'll notice now our net flow has gotten up to 20 out of factory 1. Now you'll notice, again, in this case, what's happened in the distribution center is that in fact we have received 15 units from factory 1, but we're not shipping out any. So this solution would be infeasible because we're not obeying that conservation of flow. So now let's do the following. So that's kind of the only tricky part for these models is this concept of the net flow. Now you could do this by by just simply going through and identifying like the out nodes of the DC minus the, you could say, well, okay, the ones coming out would be this one and this one out of the DC minus the quantities being shipped into the distribution center, which is this quantity and this quantity. You could do that instead of using the count if, or the sum if, excuse me, but once you just get that sum if statement set up nicely in this format, and I like this format, by the way, then it makes it pretty easy to do. You just copy it down from there. So let's now take a look at how Solver handles this. So we're going to use basically the regular solver. And so again, let's just go through the model here. We're trying to minimize total cost, which is the named range right here. It's a minimization problem, so we've pressed that radio button. The variables we're going to change are these yellow the ship range. And again, we really only have two sets of constraints here. One are these capacity constraints to make sure these 4 trucking lanes don't exceed their capacities of 50 units each. And the other one is basically that the net flow range must equal the supply-demand range. In other words, we have got to hold fast to that equality between those two. Currently, we're infeasible. It's not a feasible solution, but we're going to ask Solver to now solve that for us. Now, we of course check the box to have make unconstrained variables non-negative, which means we can't have negative flow in the reverse direction on an arc. And again, this is a linear program, so we're going to use that simplex LP option. And so we're going to hit solve, and boom, there you go. And we're going to let it keep the original solution. And so indeed, now this is the optimal solution for this problem. You'll notice all of the net flows nicely match the required supplier demand amounts. And it also, we are obeying the capacity on the trucking lanes. So with that, let me just make a few more comments here back on the slides. So we just covered the model. This gives you a little heads up about this notion of sum if. And by the way, you can just look at the Excel help. It has examples in there, the standard Excel help, in terms of how to do the sum if. Basically, sum if just says the following. Hey, only, if you've got a big range of numbers, only add up certain ones that are obeying certain criteria. So in this case, we're like saying only add it up if it's a an arc that's emerging from the distribution center, for example. So here's the optimal solution now, labeled on that sort of network representation. You can see that they are, in some cases hitting those maximum constraints on the trucking lanes, in some of the trucking lanes and not on the others. And they are certainly not overusing the direct rail links. So what's happening in this is it turns out that the trucking lanes are actually sort of the cheaper way to go in this case through the distribution center, but they are limited in terms of their amount of capacity. So it results in a solution that's actually a combination. It's multimodal in that it's using truck and rail. So we've given this example, which is very much a moving goods across a network example. And these problems are being routinely solved by companies in very large sizes. I mean, we're just dealing with one product here, but imagine you've got a lot of different products, and you've got a lot of different customer destinations, and you've got a lot of different possible factories and sources. We did this a while ago for Philips Corporation, which makes TVs and DVD players and things like that. And we did this optimization for all of their plants in North America as well as Europe to satisfy the demand for all North American customer locations. So we had factories as nodes generating products. We had distribution. We had landing points for container ships coming across the ocean. We had distribution centers spread throughout the United States, and then we had resulting customer locations which were typically like, big box retailers and things like that spread all throughout the United States. And that was a huge problem. It took a long time to solve. But obviously, operation of a distribution network like we just did and like I just talked about. But also if you're moving, things like solid waste, if you're operating a sort of a one-way supply network of you're purchasing goods from vendors and then storing them and consolidating shipments at intermediate warehouses and then sending them out to your factories. You've also got coordinating product mixes at plants. So part of what you can model into a minimum cost flow problem is you can actually have it help you make decisions in terms of which products should actually be produced at which plants. So you're bringing, in some cases, raw materials together, but then you're making them into products, which then it becomes a source node for the sort of finished product distribution side of the problem. So these things can get very large, very complex, but we want to just give you sort of a sense in terms of sort of the base model for this. And again, it falls nicely into this whole concept of optimization where we're pursuing some objective subject to some constraints, and we're asking the model to prescribe an optimal solution for us. We could build a nice descriptive model and we could go in there and propose amounts to flow across each lane, and that's again always how we start. But then we can ask Solver or any optimization engine to solve that problem for us. So with that, we're going to end this video, and this is the main problem that we're dealing with here in Chapter 6. It's really the only one I want to challenge you with in terms of problems and so forth. It's the minimum cost flow is very robust, and a lot of the other models actually nicely fit into it. So I'm good for you guys to focus just on this minimum cost flow problem as the takeaway for this chapter. So thanks for listening, and we will see you in class pretty soon. Take care.